Alright, we are going to start out by looking at nitrate, Lewis structure all the way to polarity. We're going to start out by calculating valence electrons, 5 from the nitrogen. We've got 3 oxygens with 6 valence electrons apiece, 1 additional due to the charge, brings us to 24 total valence electrons. If we start out with our N at the center, we can take 3 oxygens, surround the nitrogen, complete our octets all the way around. This brings us to 26 total valence electrons. We need to drop 2 from the count. Based on what we've done so far in class, we can take away a lone pair from both sides of where we're about to put in a multiple bond. I could have put the lone pair, or I could have put the multiple bond in any one of the 3 positions, because we've just created resonance in the nitrate molecule. Now in nitrate, we have the correct total valence electron count. We have 1 N, 3 O's, that checks out. Last check is formal charge. Nitrogen should bring in 5 electrons, and it is bringing in 4 associated. So formal charge of +1. This oxygen should bring in 6 valence electrons, and it has, 6 associated, formal charge of 0. The last 2 oxygens are set up the exact same way. They should be bringing in 6, and yet they have 7, formal charge of -1. Same on this guy. So when you take all the formal charges into account, we have -1, we have -1, we have +1, and we have 0. All of these add up to a total of -1, which they should, because the overall charge on a nitrate is -1. So this is a good structure. So let's recopy it a bit just to clear things up a bit. We have the nitrate ion, N at the center, a double bond, 2 single bonds, completing our octets, with an overall negative charge on the structure. Now I've got a total of 3 domains. We had a shortcut for this because there are 0 non-bonding domains. They're all bonding domains. Molecular geometry and electron geometry will be the same. It will be trigonal planar. Now if we look at N and O, between the N and O there is a 0.5 difference in electronegativity. You will need your electronegativity table to reference this, and you'll have one on the exam. Now O is more electronegative, so it is going to be pulling on the electrons, but due to radial symmetry, because the electrons aren't pulled in one overall direction, we can say this is a nonpolar molecule built from polar bonds, because the polar bonds cancel in terms of their pulls. Alright, hybridization, just finishing this out. Being trigonal planar in its geometry and having 3 domains, if we take our shortcut, S with 3 P's, 5 D's, we're going to use 1, 2, 3 of our atomic orbitals to get out 3 hybrid orbitals. So we have sp2 for our hybridization, which is what we always see with a trigonal planar electron geometry. We also see the typical bond angle of roughly 120 for the ideal angle. Alright, let's move on to our next example. CO, Cl2, low electron affinity goes at the center. Put our carbon at the center. Connect everything by single bonds here. So Cl, Cl, oxygen, and completing octets. Now, taking a look at our valence electrons, we should have 4 from the carbon, 6 from the oxygen, 7 apiece from the chlorines. So that's 14 plus 6, that's 20, plus another 4, 24 total valence electrons. We've got 26 in the structure as it stands. We need to drop 2 from the count. We can do so by adding in a multiple bond and choosing between the chlorine and the oxygen. Just looking at the Lewis symbol for oxygen, we've got 2 unpaired electrons, indicating oxygen is going to typically make up to 2 bonds. So chlorine would only make up to 1 bond typically. So when we put in our lone pair, or excuse me, our multiple bond between the carbon and the oxygen, we're going to need to remove a lone pair from either end, from both ends. So we end up with our COCl2. We need to do a formal charge check. Our valence electron count matched up. On the top oxygen, it should be bringing in 6 valence electrons, and it has 6 associated. Formal charge of 0. The chlorine, bottom right, is the same as the setup on the bottom left. Should be bringing in 7. It's got 7. 0 formal charge. 0 formal charge. And on the carbon at the center, should have 4 valence electrons, and it has 4 associated. So 0 formal charge. Zeros all around. 0 charge. So that matches up as well. Good Lewis structure. Now, 3 domains, just like our last example, so hybridization and molecular and electron geometries will be the same as the nitrate that we just worked through. We also have XeF4 for our next example. Xenon tetrafluoride, we're going to put the xenon at the center. Same procedure as usual, connecting everything by singles. Lone pairs to complete the octet. And let's see, everything has an octet as it stands. If we go up to the formula, should have 8 valence electrons for my xenon, and I have 4 fluorines, each having 7. That brings me a total of 28 plus 8 gives 36 valence electrons. The structure as it stands has 32. We need 4 more valence electrons. We can add a lone pair. That brings me 2 more, 4 more. I now stand at 36 total electrons. The xenon has more than 8 electrons, but that's okay because we had the extended octet rule if our central atom was on the 3rd row or lower. So, total count checks off, formula checks off, formal checks. Our F's are all set up the same, so let's just check one of these. They should be bringing in 7 valence electrons, and each one has 7 associated electrons for a 0 formal charge on each F. And our xenon at the center should be bringing in 8, and it has a total of 2, 4, 5, 6, 7, 8 for a formal charge of 0. So all formal charges add to 0, which they should for XeF4, so that checks out as well. Let's clean things up a bit, and then we can talk molecular geometry, polarity, hybridization. For XeF4, I've got 1, 2, 3, 4 F's that are connected. Whoops. Erase this guy at the center here. 4 fluorines that are attached to the center. Had an octet around each F. Also had 2 lone pairs that were sitting on the xenon. So that's a total of 6 domains. And breaking this down, 2 of those are non-bonding, and 4 of those are bonding. Because I have 6 domains, those 6 domains give me an octahedral electron geometry. But when I want to look at molecular geometry, I have to factor in that 2 of these are going to be non-bonding. So if we draw in our picture of what octahedral looks like, I've got something that looks like this. Now, these don't have equatorial and axial positions like the trigonal bipyramidal do, but let's say that I have to put a lone pair in. Well, I can put these F's in, all 4, and the way I can get my lone pairs the furthest apart is by putting them on opposite sides. So what that leaves me with are 4 F atoms lying in the same plane, so they form a square if you connect them. So my molecular geometry is going to be square, planar for my molecular geometry. Going to hybridization, the fact that I have 6 domains total is what I need to look at. Doing our shortcut, S, 3 P's, 5 D's, we're going to be using 6 atomic orbitals total. We get sp3 d2, the same hybridization that we're going to see on anything that has an octahedral electron geometry. Now as for polarity, I have essentially a xenon with 4 F's coming off in each direction, and they all lie in the same plane. So even though I have a pull of electrons towards my fluorines, these are equal and opposite, so they'll cancel. And these are equal and opposite, so they'll cancel. So because of the orientation of the bonds, overall I have a nonpolar molecule. Let's see, next up, XeF2. So instead of xenon tetrafluoride, we have xenon difluoride. Xenon goes at the center. I've got 2 F atoms. Going to connect everything by single bonds, go in, give everything an octet. So everything has an octet now. For xenon, I should have 8 electrons. For F, I've got 2 of them, 7 apiece. That brings me to 22 total electrons in the structure. Right now I've got 20, but xenon is on or below the 3rd row, so I can add in that extra lone pair on the central atom. Okay, so count checks out, formula checks out. I need to do formal charge checks. Now, F has a formal charge as it's set up now of 0, as does this F, and the xenon in the center is going to have a formal charge of 0 also. Zeros all around adds up to the overall charge of 0 of xenon difluoride. So that checks out too. Now, let's look at the geometry, move our way to polarity and hybridization. I've got 6 total domains. Excuse me. 1, 2, 3, 4, 5 total domains that are around my xenon, and 3 of these are going to be lone pairs. So if we start out by drawing our geometry for trigonal bipyramidal, which is our parent geometry, our electron geometry for 5 domains, I'm going to have 1 bond going back, 1 bond coming forward, 1 bond going right from my equatorial positions. Now, my lone pairs need a little breathing room, so we put those in the equatorial positions. My axial positions are going to contain both of my F's, and xenon goes at the center. So what I'm left with is a linear molecule for my molecular geometry, because this bond here is 180 degrees. I'm left with an octahedral electron geometry, and that was because we had 5 domains total in XeF2. For polarity, even though we have a polar bond here pulling towards the F and a polar bond here pulling towards the F, these 2 poles negate each other because they're pulling equally but in opposite directions. So polar bonds, but a non-polar molecule overall. Looking to hybridization, the fact that we had 5 domains, S, 3 P's, 5 D's, we're using 5 of these atomic orbitals, so sp3d. sp3d is the hybridization that we do associate with anything with, whoop, mislabeled here, the trigonal bipyramidal electron geometry. Mistype there, just a note. This is trigonal bipyramidal for my electron geometry, not octahedral. So miswrite a few moments ago. Okay, let's move on to our last example here. BRF3. BRF3 puts BR at the center, 3 F's coming off, completing octets all the way around, and BRF3, 7 electrons for my BR, 3 F's at 7 apiece, brings me to a total of 28 valence electrons I should have in my structure. If you look at the structure, I have only got 26 valence electrons, but I can put an extra pair on the BR because BR is on the third row or lower. Remember, that was our extended octet rule, so we can do that. Okay, so 28 electrons checks off. My formula checks off. Now we're just worried about formal charge. 0 on each F, because they should be bringing in 7 valence electrons. They have 7 associated, 0 formal charge. The BR has 7 that it brings in, 7 associated, 0 formal charge. So everything adds up to what it should. So we've got a good Lewis structure here. The next step is to take our good Lewis structure and try to get out a good 3D geometry so we can take a look at polarity. Okay. So going back to our structure, we've got 1, 2, 3, 4, 5 total domains, with 5 domains around the BR. Let's make a note of that. 5 domains. That's going to make this a trigonal bipyramidal electron geometry. Now we do have to take note that 2 of those domains are going to be non-bonding. So when we draw our structure, we're going to put our BR at the center, 2 axial positions, 3 equatorial positions. We can start filling things in. We've got 2 lone pairs. Let's put them in first. They go on the equatorial positions on TBP structures, just so they have the extra breathing room. Those are very large lone pairs. We're now going to fill in our F's. Those go in the remaining positions. Fill in our octets. Now, what we're left with, if you turn your view clockwise, is T-shaped. So our molecular geometry is going to be T-shaped. Finishing this off with hybridization. Hybridization with 5 domains, taking our shortcut. 1, 2, 3, 4, 5 domains is sp3d. So we'd say the bromine is sp3 hybridized in BRF3. Considering polarity, my axial positions are going to cancel, so my top is going to cancel with the bottom pole, because fluorine is going to have the stronger pole of the 2. So this and this cancel. But this F bond going off to the right has no equal and opposite pole. So this polar bond is going to cause the whole molecule to have a molecular dipole pulling to the right. This is a polar molecule made up of polar bonds.